First off, up on the smartboard, we need to become more comfortable with phase notations. The elements one that I bring up first, that's something that we talked about last time. Individual elements, check your periodic table. If it's outlined in black, it's a solid. Red, gas, very few things are actually liquid at normal conditions. Ionic compounds. My hope is that we can recognize at this point in the year an ionic compound, metal, non-metal, usually. Ionic compounds are either going to be solid or aqueous. Covalent compounds, only nonmetals, are usually only going to be liquids or gases. Now, why is that with the two compounds? We have to remember last unit. Remember last unit, ionic compounds have full charges, so they can really attract each other to hold together as a solid at room temperature. Because we're going to be doing chemical reactions at room temperature-ish, ladies and gentlemen. We're not going to do it at extremely high or low temperatures. Covalent compounds either have partial or no charges, so they're going to only be a liquid or a gas. So phase notations, we can narrow things down. When you see water, there's a lot of times you're going to call it a liquid, and you're probably justified in doing so. If you see carbon dioxide, hey, I breathe out carbon dioxide. It's a gas when I breathe it out. If it's created in a lab and I see little bubbles happening, it's probably a gas there also. Ionic compounds is the one we got to focus on a little bit more today. Because we are going to be doing single displacement reactions today, and next week, double displacement reactions. And those typically involve ionic compounds that are dissolved in water. The reason why we dissolve some of these things in water is it's allowing it then to surround the other chemicals, to come into contact more likely and have a chemical change occur. Because if you just had crystals of salt, NaCl, and you tried to throw it at other stuff and just mix it together in two solids mixing, they might not mix. Because there might still be attraction between the Na plus and the Cl minus. But recall, when you take an ionic compound and you dissolve it in water, it breaks apart. This should have been something that was on our test. Remember? Ionic compound, you draw dissolving. So a lot of the ionic compounds we're going to work with are actually aqueous. So we would have this type of phase notation. For example, in the little brown dropper bottles today is silver nitrate solution, AgNO3. By the way, if you get that on yourself today, which is usually the most common place is you get a little chemical on your hand, rinse it off right away. If you do, you'll be fine. However, don't be alarmed if you get a little bit of a brown stain on your hand wherever that drop went. Silver nitrate will stain your skin. If it stains your clothes, then it's there to stay, probably. But if it stains your skin, well, some skin cells die, new ones replace it, you'll be fine. So silver nitrate, though, is one of the chemicals we're working with today. How do we make a solution? We take a solid. Here's a bottle of silver nitrate solid. We add water. That's it. Remember, what does aqueous mean? When it's an ionic compound, that means I'm going to have silver ions surrounded by water and nitrate ions surrounded by water. Now, we're getting to the point where I'm not probably going to show the surrounding with water part, but I want you to realize, what does aqueous mean? It means we take a solid, we add water to it to make a solution. So I still have that chemical in there, but now those ions are floating around. And what's going to happen is those ions can react with other things. Because if you were looking at the lab benches, not only are there little bottles of solutions there, there's also solids there. Today's lab is going to be us putting solids into solutions, just adding things together. Let's see what happens. Sometimes nothing happens, sometimes something happens. So, that leads me into the next tool that we have to go over that you are given. On the way in, you picked up a sheet that looks like this. I need you to have this out. By the way, Polyatomic ion sheets on the other side. I just figured, hey, might as well just give that to you in case you lost yours. I want you to focus in on this column today. So the column on the right-hand side. And why not, where that says activity series, why not right above that, write down single displacement? So I'll explain what that chart means in a second, that activity series. But on that sheet, just on the far right-hand side, there's like a column of elements, similar to the column that you're seeing up on the smart board right now. That column is a ranking system. Part of that ranking system goes back to the trends of the periodic table that we discussed first semester, like ionization energy. How easy can the metal lose an electron? At the very bottom of that column, there's halogens listed in a ranking system as well. So how easily can nonmetals gain electrons? In a single displacement reaction, if you recall the Pogel packet we did last time, some things are going to change their charge. And just like the homework then mentioned, changing the charge is due to outer electrons being lost or gained. To truly understand why a single displacement reaction works, it all goes back to the octet rule. Elements are more stable if they have a full outer shell of electrons. Now, not everything in the world can be stable. This activity series, this ranking system that you have in front of you on the right side of your worksheet, shows which elements are most likely to become stable. Which ones are the most reactive? You can see even on mine up here, it says most active on the very top, least active on the bottom. How this works, I give you a story problem here. Near and dear to my heart. My Mountain Dew can is made of aluminum, and lead 2 nitrate's a solution that we could have in the lab. So what would happen if I accidentally poured a solution on my can? Well, first off, I shouldn't be bringing food or drinking to the lab now. See, that's just my fault completely right there. Lead 2 nitrate, if I were to write out that formula, would be PbNO3 2. Again, remember, if you don't remember your polyatomic ions, it's on the flip side of this sheet that I just gave you. Remember, lead 2 means lead's a plus 2. If I were to spill this solution on my solid can of aluminum, would anything happen? Now, first off, when you look at the two reactants of this reaction I'm proposing, again, I'll draw an arrow, but if I write down products, I'll have to write it below. If you look at the two reactants, I hope from looking at that alone, you can see that this is going to be a single displacement reaction, because it's an element and a compound. And remember that packet from last time? One of the goals from last class was, can you look at a reaction and tell me what type of reaction it is? Well, today, first off, the rest of the day today is all about single displacement, so you can kind of guess what type of reaction it's always going to be. However, today, we do need you to be aware of maybe just looking at the reactants and telling. Okay, so if I look at my list right here, I see aluminum right here. I see lead down here. When metals are in their ion form, they are more stable, because when you lose electrons, you get closer to the octet. And this is something that we covered first semester, so I understand if we're not quite remembering it, but the ion form is more stable. Okay? That means right now, lead being a plus 2, because aluminum doesn't have a charge right now, it's by itself. Lead is the more stable thing. How this activity series works is it's a ranking system. Remember, Noah, who did I have you dancing with? Was it Lexi? Yeah, Claire was gone, so it must have been Lexi. Remember that Lexi dumped her boyfriend for Noah because Noah is better, but Lexi wouldn't dump her boyfriend for someone who was worse? Again, it doesn't make sense to do that. If you're going to make a trade, you trade up. Well, in this particular problem here, aluminum is higher on the list than lead, meaning that it's going to be more likely to make that trade happen. It's going to be the thing that pairs up the nitrate. It's going to be the thing with the charge. How the activity series works is you identify the element in the compound and the lone element. If the lone element is higher on this list than whatever is in the compound, the trade does happen. Because the more reactive thing is going to become the ion form. So in this particular reaction, if I were to spill lead-2 nitrate on my aluminum can, it would react. The entire point of this activity series is for you to see whether or not things react. Because in the lab today, you're going to be mixing things together. Some things will create a change, some things won't. If I were to write the products of this reaction, aluminum is trading places with the lead. Again, I'll write my products below because I'm running out of space off to the side. One product, well, what's the new lone thing? Aluminum's no longer by itself. What's by itself now? Lead, the PB. I mean, they traded places. State of matter for PB? Solid. Oh, my Mountain Dew can's no longer aluminum, it's lead. Second product would be aluminum nitrate. But we have to rebalance that formula. Aluminum as an ion is a +3. Nitrate is a -1. So then this would be AlNO3, 3. What phase notation should I use for my aluminum nitrate? Aqueous. Yeah. Then hopefully you would notice, hey, this equation isn't balanced. I have 2 NO3s on this side. I have 3 NO3s on that side. I could put a 2 in front of my aluminum. I could put a 3 in front of my lead, which means now I got to put a 3 in front of my lead and a 2 in front of my aluminum. Let me go over another problem. Man, am I a klutz today. Now I took my wedding ring, so I'm going to get in a lot of trouble for this, and I dropped it into lead-2 nitrate solution. What's going to happen? Well, if I wrote out my reactants, I have my PbNO3 and I have gold. If the lone element is higher on the list than the thing it's going to replace, gold would replace metal if it could because they're both metals. If the lone element is higher on the list, the reaction occurs. My lone element is gold. Look on your sheet. Gold, Au, is at the very bottom of the list. Lead is above it. Can gold replace lead? Is the lone element high enough on the list? No. This is, instead of Lexi dumping her boyfriend for Noah, she's dumping her boyfriend for the exact opposite of Noah. So, short, not blonde, doesn't have chemistry with them. Just, there's no reason to do it. This reaction won't occur. So in other words, I could take off my gold ring and I could throw it into a vat full of lead nitrate. It'd be perfectly fine because it won't react with it. Heck, notice the bottom 3 things on this list. Gold, platinum, silver. Aren't these all the really expensive metals? Isn't this a good thing that they're in the bottom of the list? Because if they're at the top of the list, they get in contact with any type of chemical, they're gone. They'll react with things. They will go away. I mean, your list even has H2 on it, doesn't it, at some point? Right above copper, it has H2. H2 is going to be for the hydrogen from acids. I could put my wedding ring in acid and nothing would happen to it. When I student taught, I had my cooperating teacher do that. He'd take off his ring and put it in acid. Nothing would happen. Of course, you'd have to rinse it off really good before he put it back on his finger, or else then his finger would get that chemical burn. But this list shows the lone thing has to be higher than what it's trying to replace. So we are going to have you practice this a little bit. Let's pause this first off.